Well, thank you, Pauline. I find myself here with very few credentials as far as steam engines are concerned. Although within the slavery studies which I've been looking at, we do have some interest in stationary steam engines, which were powering the mills on the sugar plantations and led to the use of triple effective apparatus and things of that kind in the prehistory of chemical engineering. But that's my only link. I see locomotives as being much more at the sort of sexy end of the engine spectrum. As soon as the wheels start going round, it's much more interesting, and it grabs the heart and the mind of the of people. The job of chairing a lecture here is very, very easy. I just say something to introduce the lecturers, and then they get on with it. And then if they've left time, I come up and let them answer some questions. Well, our two speakers are very well known within the history of chemistry community. We have John Hudson. They're both academics, of course. John Hudson, who taught at Anglia Ruskin for many years in chemistry. And then towards, I think, what he would call his latter days of employment, he decided to do something in history of science, and he registered at the Open University to do a PhD. And that really is the embryo of tonight's lecture. So John, well known within the history of chemistry community, certainly still working with that community as treasurer and membership secretary of the appropriate group within RSC, etc. Our other speaker, now when you Google Colin's name, you come up with pages and pages and pages, because he must be one of the most productive authors in the history of science community. When you look at his CV also, you see the names of all the places he taught in or studied in have all changed. They've all changed status over the years. He is, in fact, he studied for his London External BSc at what was then University College Hull, and went on to teach at Kingston Tech and other places as a chemist. But he's best known for being the foundation professor in the Open University Department of History of Science. And it is as a history of science scholar that his reputation has been built. He is, I fear, the walking doyen of that community. And we were having words earlier as to whether I said that he was more than 80 years. And he said, well, if you must. So I've let that cat out of the bag. Colin has also published very widely at the interface of religion and science, and that has been a subject where he has added again to the literature in considerable volume, addressing many of the questions of today. You haven't come here to listen to me, you've come here to listen to Colin and John, and I give Colin the first opportunity to come and stand behind the lectern. Thank you.
Well, thank you very much. I don't recognise that last chap he talked about. Anyway, good evening, ladies and gentlemen. We're here to introduce and to celebrate a new book, a book which actually has been published by the Royal Society of Chemistry a few months ago, but still this year. That is the cover of the book, and its title really is Early Railway Chemistry, which seems certainly to be a strange contradiction in terms, railways and chemistry, but as we shall see, it's not so. Now, the authors are Colin Russell and John Hudson, one of whom was a railway enthusiast from his youth, and the other grew up into it. The way we combined forces was at the Open University. Both of us are chemists, both fellows of the Royal Society of Chemistry, but one of us, me, had done quite a bit of work on the origin of railway chemistry and had discovered quite a bit about it that nobody seemed to know. And it became clear that there was a vast amount of work to be done, far more than I had any chance of doing at all. And to cut a long story short, we recruited in the university a very able young chemist, John Hudson, to do a PhD. And this he did, and he produced it and was awarded it in 2004. So that's the background of the book and the authors. And go back to this dated picture. It's actually a clip from a film taken in 1983 of a special train from York hauled by a very special engine. And the engine is called, for technical reasons, the Midland Compound, and it's quite old, and it was a product of the department in the Midland Railway, headed by a man called Richard Dealey. And this is sometimes called a Dealey compound. And Richard Dealey was the most interesting man in that he was not only a very good railway engineer, he was the chief of the Midland Railway, but also he was a very good amateur chemist. And he did a great deal of exploration in chemistry, and he published a number of things, but above all, he was co-author of a book on the chemistry of lubrication, which of course is important for railways and important for all engineering projects. So that's why his engine is on our cover, because it's not his designer, but his father-in-law, as it were, was Richard Dealey, a chemist as well as a railway engineer. Here is the same locomotive on the same train, perhaps 3/4 of an hour later, in Todmorden, which is on the Lancashire-Yorkshire border. And it's a steamy but successful engine. Now, the vapours and the effluents may not please environmentalists very much, though steam never hurt anybody, but it's very successful. In fact, that locomotive is 80 years old, or was then 80 years old, and is still going strong, in fact, from its home in the National Railway Museum. But the Midland Compound illustrates, just one tiny illustration, something of the progress of railways since what I'm going to call the Railway Revolution. The Railway Revolution really was about 1800 to 1850, during which time things like the rocket and so on were replaced by more and more sophisticated engines, and by 1850 they were quite recognizable as, of course, steam engines. There was no other form of propulsion. And the Railway Revolution is one of the things that's quite important for our story. It started with a recognition that if you really want to move lots of material, heavy loads, quickly and efficiently, then you've got to use something like a metal on metal, metal wheel on a metal track. And you can see there the enormous improvement that you get in going from a horse and cart, say, to a cast iron tramway. And of course it improved greatly after that. But the Railway Revolution actually had some very important effects. I just mentioned 4 of them: population mobility, railway time, holidays for all, and the transformation of industry. Now, this is how, if you are a member of the crowd in the early days of railways, it must have seemed when you were queuing up for a ticket, as the crowds surged in and the railway trains were often extremely full, and there were many of them going to popular resorts. Perhaps that's not the best way of proving my point, but that statistical graph from the British Office of Statistics makes it clear how greatly the railways increased in mileage and in passenger numbers, up to and well over 1 million. But there was a second effect, and that was this business of time. Station clocks are obvious to everybody, but often, usually in fact, station clocks in one town differed from those in another at the same time because of local time variations. And this became quite bad when the main line from Paddington to eventually Cornwall took place, and the difference there in time was 20 or 25 minutes, which meant that if you were going to change trains, you were in some problem about time. And so, to cut a long story short, all railway times were eventually unified into Greenwich Mean Time, sometime after the 1840s, and then they became the time which everybody adopted in the town. They became the national time, not just the railway time. And that was a big social effect, because it did affect the way that people could communicate with each other, and it was entirely due to the railways. But there was another thing. Holidays for all were invented by the railways. We take them for granted so much, but it was in fact the case that the railways promoted visits to the seaside, as for example this one to Blackpool, where amongst the attractions were not only sand and the Blackpool Tower, but various other things as well. And the railways were keen to capitalise on this, and as a result, holidays of a week or a fortnight in the summer became the norm for vast numbers of working people. That's a huge social change, and it would never have happened had the railways not been able to carry vast numbers of people to desirable spots in the summer. But perhaps most of all, in the question of transport, and the transport of raw materials to factories, of their products to other places, many other places over the country. And food is an example. You could take freshly caught oysters or lobsters or anything you liked at one town, put them on a train, and they'd be at another one a few hours later. In other words, people would begin to eat things that hadn't grown up with them. This is a totally new transformation, and again, it's largely due to the railways. There was no road system, nothing like that, no alternative. So I conclude that railways have always been, and certainly were in the early days, a major instrument of huge social change. But at the same time, and this is most peculiar, there was another revolution taking place, which also had, as most revolutions do, big effects on society. And this was what is often called the chemical revolution. It started in the 18th century, late 18th century, and finished around 1850, insofar as it did finish. But what the chemical revolution did was to make possible a new understanding of how chemistry worked, of how chemicals were made and how they reacted. And the chemical revolution was the beginning of our modern understanding of chemical compounds. Now, that may not strike a railway person as very important, but you'll see it was. One great chemist of the 19th century, late 18th century, Berzelius from Sweden, was very keen to initiate something like a chemical revolution. And he argued that you had to have fire in order to find out what was going on. And of course, he had plenty of experience of that. Castles were set light in the political revolutions, cottages, churches, palaces, and all sorts of other things. And eventually, the chemical industry became renowned for its factory chimneys and its belching out of materials. Now, from that, it's pretty obvious that when you burn something, something is given off into the atmosphere. You can see it, you can feel it, you can smell it. But, in fact, that was not the case. Well, something was, but that wasn't the essence of burning. The essence of burning was rather the taking up of a new material called oxygen. And many people were important in this. The English chemist Joseph Priestley discovered oxygen, although he didn't believe it, but he did discover it. Lavoisier worked out from the products that he got and from the things that gave them a list of what he called elements. And these elements were quite new. They included largely metals. And it was the English chemist John Dalton who thought of the way in which these metals might each have its own specific kind of atom. And not just 3 or 4 sorts of atoms, but as many atoms as there were elements. And from them, he came to atomic weights. And it is a fact that by the mid-19th century, some of the basic features of the elementary chemistry we were taught were becoming acceptable, and the chemical revolution had taken place. Now, one advantage of all this is that it was possible now to analyze materials which you couldn't have done before. You could say that this has X% of that and Y% of that. And this became a very important thing for the railway revolution. And I have to say that it led to the coming together of like-minded people in Britain, and the Royal Society of Chemistry, or rather the Chemical Society of London, was founded in 1841 on the basis partly of the analytical work that chemists could do. And one of its early homes, and eventually its later home, was here in Burlington House. Now the question we have to ask is, what happened after that?
Okay, I'm going to sit there.
Okay.
Okay, all right, let's go back.
That's right.
Right, so... Oops. So I don't think I'm being very successful here. Okay. I'm on there. I'm on there. Right, okay, thanks. Well, Collins talked about the railway revolution and the chemical revolution, the two came together. I've lost the slide again. I've lost my slide. Oh, there we go. The two came together in September 1830. This was the great day when the Liverpool and Manchester Railway opened, the first railway in the modern sense, in that one respect was that it used steam traction only. The horse was out of date. But 6 weeks before this railway opened, the directors consulted a chemist. That chemist was William Henry, a chemist in Manchester, a medical man, and the reason they asked his advice was they wanted to know whether the quality of the water that they were considering purchasing for their locomotives was appropriate. Now, we might ask ourselves, why was water quality so important? Well, of course, you all know if you have hard water in your kettle, it furs up. That had always been a problem. Stationary steam engines, of course, preceded locomotive engines. But one of the great technological advances that occurred at this time was, as you can see with the firebox there, the hot gases rushed down the boiler tubes into the smoke box at the end, and the external surface of these tubes heated the water. Previous locomotives had just one flue going down, and that didn't supply steam at an adequate rate, and earlier locomotives simply ran out of steam and stopped. These locomotives, starting with the rocket, could chug all the way from Liverpool to Manchester without running out of steam, and that was quite an event. But if the scale forms on the outside of the tubes, then of course the thermal conductivity is reduced, and you're back to the old problems. You don't generate steam at a sufficient rate. So it's very important to get water of the right quality, and if the boiler furred up too much, then it was a very expensive, difficult job to get all the scale off the outside of these little tubes in the inside of the boiler. Another reason possibly why they were so keen to get analyses was there were boiler explosions occurring. And this is a cartoon of 1831 called The Pleasures of the Railroad. And boilers did blow up. It was thought it could be due to the deposition of scale and fur. More probably, most boiler explosions were due to weakness of the boiler barrel, or the engine man actually weighting the safety valve to get a higher pressure of steam. But obviously, the railway companies wanted to do all they could to allay public fear about the new form of transport. And several railway companies, many of the early railway companies, didn't bother to get water analyses, and they found out at their cost that this was a very expensive mistake. But after about 1846, it became the norm for railway companies to get water analyses. And this happened because this man here, William West, who had developed a very considerable consultancy business in analysing water for railway companies, gave a presentation to the Institute of Civil Engineers on the importance of railway engineers getting water analyses done. Present at that event were Robert Stevenson and many other well-known railway engineers. And after then, it was the norm for railways to get a water analysis done before they laid on a water supply. Companies like Newcastle and Carlisle and London and Birmingham before that had not got the water analysis done, and they had all sorts of breakdowns and problems as a result. One other chemist I might mention who did a lot of water analysis for railways and a lot of other analyses for railways was Edward Franklin, a sort of slightly later date in the mid-1850s, and Colin has written the standard biography of Edward Franklin, as many of you probably know. But Immediately, chemists started to do other things for the railways. Railways purchased fuel in enormous quantities, coke and coal. They analysed coke and coal, so the railway company could choose the best supplier. They also analysed air quality in tunnels. Another problem, another fear of the travelling public for the new method of transport was, were they going to be asphyxiated in the tunnels? Well, the chemists came along and analysed the air quality after trains had gone through and decided that, in fact, the air quality was perfectly okay. In fact, they also got doctors to look at the air quality, and at least one doctor said that the air quality in a tunnel after a train's gone through is positively beneficial to people suffering from milder forms of pulmonary complaint. He was, of course, a paid consultant. Another service that the chemical consultants could do was advise on timber preservation, methods of timber preservation, and analysing the preservatives. In the 1830s, this was before the days of creosote was really available in large quantities, and salts like copper sulfate and zinc chloride, and particularly mercuric chloride, were used in huge quantities. There was a lot of timber was used for things like turntables and stations and viaducts. This was before the days of steel, mass production of steel. So a lot of railways were thrown up very quickly, and a lot of timber was used. Mention one other chemist, and I call him a chemist, who advised railways, was Michael Faraday. He was a great friend of Brunel, and he advised Brunel particularly on timber preservation and analysed some timber preservatives for him. Brunel wanted Faraday to work as a consultant, but Faraday refused to accept payment. At this stage, it's about 1836, he was asked, he wanted then to concentrate on fundamental research. He did some analyses for Brunel, but purely as a favour, and he wouldn't accept payment. So the chemists from the very early days, from 1830, from the dawn of the modern railway age, were performing important functions for the railway industry. But no railway company was needed the services of chemists to a sufficient extent to even think about setting up their own laboratory and employing a chemist or chemists on a full-time basis. But all that was to change in the early 1860s, because a new technology came along. It was a technology of steel production on a large scale by the Bessemer process. Steel, of course, was known before this, but it was made in small quantities, mainly by the crucible process, and it was a special and expensive metal. But Bessemer found a way of making steel on large scale relatively cheaply. And it was obvious that steel was the material of the future. It was going to replace wrought iron, which had been very widely used. And one company, the London and North Western, which by then was a big railway company, decided to open its own steelworks. Now, if you had a steelworks, you needed a chemist. You needed a chemist to analyse the pig iron that went into the Bessemer converter there. You needed a chemist to analyse the steel that came out for its carbon and manganese content. So it was important to have a laboratory there. So the London and North Western Railway opened the first chemistry laboratory associated with a railway company in the world at Crewe in 1864. And that is where railway chemistry in the railway companies actually started. But very quickly, the chemists in the Crewe laboratory made themselves very useful around the works. And the guy in the middle there, in front of the door, with the, they've all got beards, but the guy in the middle there, the back row, Joseph Redrop, was the man who, more than anybody else, showed the company what chemists could do. He would analyse anything and everything that the company bought to see they were getting good value for money. And very quickly, this was only taken about 15 years after the laboratory was established with one chemist. There were 7 there. There were 5 chemists, the laboratory attendant and the photographer. Railway chemistry had really arrived. And the other big railway companies were convinced by the success at Crewe of the value of opening a laboratory and appointing chemists. And as a result, between then and the First World War, all the big railway companies in this country established their own chemistry laboratories with their own full-time chemists in employment. Of course, up to grouping, when the railways were grouped together in 1923, there were about 120 separate railway companies, but there were just a few big ones, and all the little ones were, nearly all of them were allied or associated with a big company in one way or another, and they, if they needed analyses, they got them done by the big company. So railway chemistry was the norm. What did these chemists do? Well, I've talked a bit about quality control already, but as well they did what I call analytical research. They were doing chemical analyses all the time, so they developed new methods of chemical analysis for the work they were doing, and they contributed to analytical chemistry in this way. They were involved in safety considerations, and they also did research on railway issues as opposed to chemical issues on railway issues. So let's look at the quality control very quickly, not concentrating on the methods, but these were the analyses done in one laboratory with 6 chemists over a 6-month period from July to December 1910. A phenomenal output, really, because don't forget all the chemical methods then, what chemists call wet methods. Not these days, if you want to analyse steel, you just stick it in an instrument and press a button and it all comes up on a computer screen or something like that. This was slow, painstaking, gravimetric work, and really that's phenomenal output for one laboratory with six chemists. I'll say a little bit about traffic samples in a minute, but the rest are obviously various things that were acquired by the company. Just very quickly, I mean, if a company acquired a material that was substandard, of course it could have catastrophic consequences. This was an accident at Waterloo Station near Liverpool, not Waterloo in London, in 1903, I think, where a spring hanger, one of the spring hangers on the locomotive fractured, the locomotive went down on one side, turned round and the train piled up behind it. I don't think anyone was killed or injured, but it was due to a faulty steel component. So it was very important the company not only get good value for money by analysing the materials they purchased, but it could have serious safety implications if the materials were substandard. I mentioned that chemists contributed to analytical research. This is just a very quick table of a few papers that were published by chemists in the chemical literature, by chemists working for railway companies. I mean, there were many more. I might just, manganese and steel was a standard method when I was an undergraduate. I had Vogel's Quantitative Inorganic Analysis, 3rd edition, and the manganese and steel method was there. It didn't say it was developed in a railway laboratory, but it was developed in a railway laboratory. So they made some very important contributions to analytical chemistry. And as well, one of the railway chemists actually published a book of analytical methods. He called it Engineering Chemistry, all the analytical methods that would be used in engineering or railway laboratories. Joshua Phillips, he was assistant chemist at the Great Western Laboratory, and then he moved to set up the Great Eastern Laboratory at Stratford in London. So this quality control and analytical research was the most time-consuming aspect of their activities. But I mentioned safety issues, and I mentioned that very quickly, but railway companies were, of course, in competition, but of course they had to meet together for matters of mutual interest. And there was this body called the Railway Clearing House in London, which was established in 1842 for principally, initially for division of revenues, where people travelled across the country from one company to the other. But they met on matters of mutual interest, and obviously the packaging and labelling and carriage and safety precautions associated with dangerous materials were a very important matter. That was initially done by the goods managers, but as things got more technical, they called upon their chemists, and in the end, the goods managers really had nothing to do with it. Always the committee, this is the committee of all the chemists about 1916. Initially, they always made recommendations to the chemists, to the goods managers, but in the end, the goods managers just rubber stamped them because it was really far too technical for them really by that stage. And this same guy who written the book on engineering chemistry, on analytical methods, also wrote a book which he called The Handling of Dangerous Goods. And that's one of the earliest safety manuals, I think, and it's the only safety manual I have ever read which you could say is a good reader, because he had this huge chapter on what he called instructive accidents, which were not always railway accidents, and he has a sort of particularly gory turn of phrase. Just to quickly quote one example, a dangerous material then, of course, was paraffin oil and paraffin lamps. And he refers to an incident where two guys had an argument, and one guy picked up the paraffin lamp and threw it at the other guy, and it missed, bounced off the wall, came back and landed at the assailant's feet, broke, burst into flame. The assailant was covered in burning paraffin oil, and as Phillips, the author, commented, he died in horrible agony. If we go on to research on railway issues, I'll just point out two or three really important things these chemists did. Now, Colin has mentioned Dealey, Richard Dealey, at Derby. The chemist at Derby, Dealey was a chemist as well as an engineer, but the chemist at Derby, the chief chemist, was a man called Archbutt, Leonard Archbutt. And between them, they developed a new method of water softening. They said how hard water was a problem. Well, if you can't get soft water, you've got to soften it. And they devised this method. Whereby they had three, just to mention, at Derby, for example, they need 500,000 gallons a day of water. That's a heck of a lot of water. And they devised this method of 3 tanks of water. First tank, hard water in, added the softening chemicals, stirred it up with steam. But at the bottom of the tank was the bit of the sludge, because you precipitate the hardness. There was a sludge left from the previous operation. And as those of you amongst you who are chemists will know, if you want to get something to crystallize, the way to do it is to seed it. Well, this sludge acted as a seed. The crystals formed more quickly and were bigger. So the next half hour, the sludge, the new crystals settle down, and then in the next half hour, the relatively soft water was piped off, some of the sludge was piped out, and then the whole process started again. They'd get 30,000 gallons an hour like this. This was patented, it was used throughout the Midland, it was used by other railway companies like the Great Western and the Great Central, and it was used by a number of industries outside the railway industry. One or two other items of research. Go back to our diagram of the locomotive boiler. What they were finding at the end of the 19th century is the copper fireboxes were abrading far more quickly than they had before. In 1850, a firebox might be good for 500,000 miles. By 1900, a new firebox was often shot at the end of 100,000 miles. Why? What the heck was happening? Well, the reason was that the copper they were purchasing was now much purer, because the infant electrical industry wanted the purest possible copper, because the purer the copper, the better a conductor it is of electricity. But, of course, the purer the metal, the softer it is, so the fireboxes wear away more quickly. So the question was, what was the impurity, or what were the impurities that were giving the necessary hardness? And that wasn't an easy issue, because when they analysed the copper, the old copper and the new copper, they found that the old copper contained at least 12 extra elements there in small quantities that might be responsible for hardening the firebox. They found that arsenic, which is naturally present in copper, both from Cornwall and Anglesey, was the essential hardening element. And that was also important for the boiler tubes as well, going through the boiler. What they also concentrated on was these stays here, the Firebox Stays. You see the stays there. They pin the boiler, or they pin the firebox to the outer casing of the boiler. And don't forget that boiler's got water in it under high pressure. So those stays have got to hold that firebox to stop it imploding. If a group of stays together fail, then the consequence is a dreadful disaster. This was an accident about 1903 where a group of stays has collapsed. The superheated water's gone onto the firebox, the coals in the firebox, a massive explosion. And this is just the boiler. The actual frames and the wheels are literally 100 yards down the track. So chemists also worked on the best composition for the stays. And of course it became more and more important because by this time boiler pressure is about 200 pounds a square inch. In the early days of the railways are more like 50 pounds a square inch. Intuitively you think you want the hardest possible stay, the toughest stay. But actually that was wrong because as a firebox expands and contracts, if you've got a very hard stay, then what actually it does, it just saws a hole where it's pinned through the firebox. You wanted a strong stay, but it had to be slightly softer than the firebox, and that was the trick. And again, the chemists discovered that. What else did they do? Well, this is another boiler explosion. There are two types of boiler explosion. This is completely different, as you can see. The firebox is still there, but the boiler isn't. The boiler barrel has just completely burst. And the chemists worked on this as well. You can see the tubes there. That wasn't so serious. I mean, the footplate crew weren't killed in that case. It would have been bad news if you'd been standing on the platform next to that one, but I think this happened in the yard. But the boiler barrel burst through corrosion. And as boilers expanded and contracted, you've got little grooves developing which act as galvanic cells, centre of corrosion, and that could lead to an explosion. Chemists worked on the salts in the water, not the ones that cause hardness, but ones which might aid corrosion, but and therefore tried to make sure that water supplies didn't contain these salts either. But the real mechanism of corrosion, understanding the electrochemical method of corrosion, was really sometime in the future. This was 1877, this particular explosion. One other kind of disaster that chemists worked on were broken rails. Broken rails have been a problem in the railway industry all through, up till the present day. But this was a disaster in 1895 at St Neots on the night express to Edinburgh. 2 people were killed here. But when they analysed the rail, it was perfectly within the specification. The chemical composition was okay. The problem, of course, was that the microcrystalline structure of the rail was wrong. And this was the result of the manufacturing process of the steel in the steelworks. Now, this was all relatively new at the time, and chemists immediately started using the techniques of metallography to look at the microcrystalline structure of the metals that the companies were purchasing in an attempt to make sure that metals were not samples were not purchased which had structures which could lead ultimately to disaster. One final kind of research that I'm going to mention that chemists were involved in was lubrication. This is an oil testing machine that was used in the Darby lab. Again, Archbutt and Dealey were doing this. And they not only investigated methods of analysis of oils from a chemical point of view, but they very much did some very fundamental work on the mechanism of lubrication and how additives to oils produce their effects. And Collins mentioned the absolutely seminal book that Archbutt and Dealey of the Midland Railway, Dealey being the engineer, Archbutt the chemist, produced. This went to 5 editions, and it was the standard work, standard text on lubrication between, this is the second edition, between about 1900 The 5th edition was 1927. It had at least a 30-year life as being the book on lubrication. So quite obviously, the work that the railway laboratories did increased enormously from the time they were first established in 1864. That's when the laboratories were established. The consultants worked from 1830. And this is the staffing levels at one laboratory, one of the larger ones, Derby, between 1877, when that lab was established, and 1922, when the companies were grouped together into the 4 large groups. And you can see it ended up with started with 1 chemist and ended up with 13. And that was typical. Swindon was another big laboratory, Crewe was another big laboratory. They all had about 13 chemists by the time of grouping. Overall, with 14 companies having labs, by 1922, which is when my detailed research stopped, there were about 100 chemists employed full-time in the railway industry. So it was quite a big effort. The facilities that the railways provided also changed. They tended initially just to stick the chemists in any old shed that they had lying around the works that wasn't being used. But as the chemists proved their worth, so the facilities improved. This is the Darby Laboratory about 1900. You can see it's very cramped, but it certainly wasn't the first home. It was the second or third home at Derby. But in 1913, the Midland Railway provided the chemists at Derby with really what was state-of-the-art facilities. This photograph is 1946, but the laboratory was provided in 1913. And this was the general laboratory, but there was also an oil testing laboratory, one for copper, one for steel, one for various other specialisms as well. So they were pretty good in providing really first-rate facilities. So that's a very, very quick look at what the chemists did over the period 1830 to 1922, a period that we call the period of early railway chemistry. And over that period, railway technology changed from this, the rocket, to the castle locomotive, which was prototype of which was wheeled out in 1923, actually. An enormous change in one human lifetime. Now, Colin and I wouldn't take away anything from the engineers. I mean, phenomenal engineering achievement. But our point, the point we are making, is that working with the engineers, alongside the engineers, were the chemists. And without the input of the chemists, this development, we maintain, could not have happened. And it's an interaction which we feel has not been adequately recognised, or has not really been recognised hardly at all in the past. So the purpose of our book is hopefully to put the record straight. Thank you. So I'll just get it ready for you, Colin. Escape. Here he is. Just wait until on the screen.
Well, thank you, John. If we'd gone a bit further into the modern age, we'd have met diesel engines and electric engines, and we would have learned something of the way that modern chemists have saved an enormous amount of money for the railways. And I can think of at least 2 projects where £1 million a year was saved by the application of chemistry to diesel engines. And so it may seem they all lived happily ever after, the railway people and the chemical people. Indeed, the great James Watt, who preceded railways, actually regarded himself as a chemist, and he thought that engineering was a subdivision of chemistry. That's not a bad idea, actually, but unfortunately it didn't hold. And in fact, what we find is something very different. And what we find, and with this I close, is the sad fact that historians of railways and historians of chemistry don't talk to each other, and that there appears still to be in the railway community an almost total unwillingness to admit that chemistry has done any good, and yet it has made the railway industry possible. And it's part of the self-image of the railways, and one of the illustrations of that is the number of books and things that come out from the railway press or from people who work for railways. Now this book here is a magnificent book published about 10 years ago and written by Edgar Larkin, who spent most of his working life in railway workshops. And this book, which is magnificently illustrated with line drawings and photographs, aerial photographs, and many, many other things, doesn't mention anywhere even a chemistry laboratory. And the detailed plans of chemical works, of railway works, show nothing at all of the chemistry, which is very sad, because otherwise it's a magnificent and superb book. Last month, the Railway magazine did something rather similar on a more modest scale, and they had a souvenir issue about locomotive builders in Britain, and they went over the same ground to some extent as Larkin, and again, chemistry was completely passed over. And in the 1930s, there was published by the Great Western Railway a series of books written by a man called Chapman on their behalf, and they were clear propaganda for the GWR, and they were brilliantly written for boys of all ages, as they called it. And the Cheltenham Flyer was one of them, then the world's fastest train, and all the details of how the engine was made and the train was run, they're all there, but no chemistry. And there were 4 or 5 other books in that series in the 1930s, which together sold 100,000 copies in Britain. So the message was widely distributed. But sadly, nothing about chemistry. And one is left with the big question, why? Well, I can't go into that now. There isn't time. But in the book, we do try to come up with some suggestions as to why this great gap has existed for so long. And I conclude with this famous locomotive, Mallard, another steam locomotive and a product of Sir Nigel Gresley. And on the 3rd of July, 1938, it achieved a record-breaking run of 126 miles per hour down Stoke Bank near Grantham. It was a world record that has never been beaten, and it's still held by Mallard, which still can run. And Mallard had all kinds of improvements. It was a 3-cylinder engine, along with others, and this one had a double chimney and various other things. But one factor is never mentioned. Gresley's works, LNER works, had in his department a sub-department of chemistry. It wasn't called that, it was about lubrication, but in fact it was about almost everything else that was chemical. And Gresley was very friendly with the members of the chemical staff. And there is no doubt that Mallard ran down Stoke Bank with many, many gallons of oil which were made at the Gresley works. Oil which was invented by the chemists, formulated by them, and probably actually put together by them. And as she went downhill, I wonder if anybody who watched her wondered anything at all about the work of the chemists who had undoubtedly helped to make the whole achievement possible. Well, there's much more to be said. We say it in the rest of the book, and we go to the present, to something like the present day. And we can only say that we thank you for listening so patiently to us, and we hope that you will find the book is of some interest and some help. And one vital question emerges: is the railway industry going at last to recognize formally that chemistry plays a vital part? Because if it doesn't in the future, it has really no future at all. But I believe it will. Thank you very much indeed.
Well, certainly the chemistry flag has been waved enthusiastically this evening, and so at least to this audience, the history has been put right in terms of the chemistry contribution. Our speakers are pleased to answer questions for a period, and if we have such, I believe there are some roving microphones around. Yes, two RSC colleagues are waving them. If anyone would like to ask questions, please do. If you want to name and give your affiliation, fine. If you want to remain anonymous, also fine. So can we have any questions? The microphone will reach you in a moment.
Thank you. My name is John Buquette. I think what you've neglected is a lot of work was done by the supply industry. You mentioned wood preservation. A lot of the early work was done by a firm called Burt Bolton and Haywood, who indeed established their own tar distillation plants to produce the creosote. And I think coming right up to the modern day, more railway chemistry is done in the supply industry than actually within the railways.
Can I take that one? Well, I wouldn't totally agree with what you're saying there, that what actually happened is in the earlier days, the really early days, more of the chemistry was done by the consumers rather than the producers. I mean, not to take your example of timber preservation for the moment, but to take the example of lubrication. In the early days, the railways bought the oil themselves, they mixed and formulated the oil themselves. Later on, the fundamental research in lubrication and in producing oils passed from the consumers to the producers. For example, what became BP established their research establishment, I think, at Sunbury in the middle of the First World War. Prior to that, a lot of work had been done. By the consumers themselves. So it kind of changed over this rather long period and the producers began to do the research, and through not only individual companies but things like research associations, non-ferrous iron and steel, non-ferrous metals and so on, had their own research associations. So you tended to get the research passing out of the hands of the consumers in the way that you've described. I think we've come back in the way that you describe. But in the very early days of timber preservation, it was the railways who decided what they wanted. I mean, obviously, I had to give a very brief presentation, but the North Eastern Railway actually commissioned its own, back in the days of consultants, actually commissioned a consultant called Thomas Richardson to do a very extensive series of research on various different timber preservatives. This was 1859. He went into all these things, and by then, coal tar creosote was beginning to come in a big way, and he came down on the side of that. But right in the early days, it was the consumers, probably I think more than the producers.
Yeah, I would thoroughly agree with that.
Do we have another question?
David Dale. Obviously, the railway companies were keen not to have explosions and problems like that, but was there any regulatory system, governmental or otherwise, which oversaw the safety precautions that the chemists had a part in doing?
So are you saying was there a regulatory body?
Was there any sort of regulatory body, either from the railway owner's side or from the government side or from any other?
Yes, well, there was from government, yes. Very definitely. From 1892 particularly, there was the government... well, first of all, there was the Explosives Act, which I think was 1875, as explosive materials were carried by the railways. But then, in the early 1890s, the railways got out what's called a special classification of dangerous materials. But that was done partly at the behest of the requirements of government. So the government certainly kept a kind of a watching brief, and as far as explosives were concerned, they kind of really took the initiative back in 1875. So yes, there was a great deal of government pressure, if you like, on the railways, both for regulating carriage of dangerous materials and also for things like charging rates and so on. So yes, there was government involvement in the whole business, and I mean particularly like when petroleum came in, for example, in a big way with the internal combustion engine, then the railway chemists helped in the design with the engineering colleagues of tanker wagons, but then government inspector then looked at the designs as well. So it was a kind of partnership between government. The relationship was pretty complicated in a way, but there was a partnership. It wasn't the railway, and perhaps I gave the impression the railways were acting on their own in this. No, they weren't. There was certainly government involvement certainly from about the 1870s onwards. In the very early days, the railways used to refuse really dangerous materials. They wouldn't take concentrated sulfuric acid, oil of vitriol, as they called it. But the pressure from the chemical industry was such that they had to agree to take these materials, and that's when they started to suggest safe methods of transport.
Thank you.
I think there was another hand up earlier, but we'll take the high hand.
Hello there, Andrew Robbins from Network Rail. You've spoken very interestingly about the contributions of the chemists to the development of railway technology. Did the requirements of railway engineering in turn drive innovation in chemistry technology that spread beyond the railways?
I didn't quite hear it.
Yes, is there a reciprocal of the benefit, so that railway chemists had general methods which went out into other parts of industry? I think you did touch on it, actually.
So if you're asking if railway chemists had methods that went out into other parts of industry, is that what you're asking?
No, sorry, I was just asking, did the railways spur innovation in chemistry as much as the chemists has helped the railways?
Did the railways inspire innovation? Well, yes, they did, in as far as particularly the analytical methods and so on. Yes, they did. I mean, any chemical, or shall we say, any industrial concern that depends upon chemistry for analysis or any other service is, in turn, going to spur development in chemistry. And yes, I mean, I did touch on it with Phillips's engineering chemistry book. There were, I can't give you a number, but there were, literally dozens of published methods in chemistry which were developed in railway laboratories. I mean, just to expand on very briefly on one particular one, which was on my table. If you may remember from, shall we say, those who are of my age or Colin's age, you may remember in your school chemistry of picking up a bench reagent and it was 2 normal sodium hydroxide or something like that. The idea of having bench reagents of a sort of simple whole number ratio of equivalent weights per litre normality was developed in the railway workshop. They called it the E method to equivalence, whereas normality before that was supposed to be standardised solutions for volumetric analysis. Every wet chemistry laboratory in the world adopted that system, except we now do the related method of molarity. But, that is an example of every wet chemistry laboratory in the world, I guess, adopted that, and it came from the Crewe laboratory in 1877. So, yes.
And another one was the famous sodium bismuthate
manganese, yeah.
Test for estimation of manganese. And the first reaction as a young chemist I ever had to do was to do a bismuthate test. And it took ages and ages and ages. And only years later I learned that it had started with the railways.
Yeah. We had another question in the middle of the block. Your hand is now up, yes?
Yeah, maybe this is really a follow-on question to this lecture, but what do you consider to be the major role of chemists in the development of railways now and going on into the future, very broadly? What's the progression?
Shall I answer that?
What's he asking?
Role of chemists now. Well, I'll start and you can... my own view is that I won't say we've gone backwards. That's quite wrong. Chemists, of course, are still involved. As indeed chemists are involved in just about every aspect of modern technology. But chemists are not employed directly by the railway industry anymore. They haven't been employed directly by the railway industry since 1996, when the railways were privatised and the chemistry laboratories were sold off to an independent company that does analytical work, and that company still does some work for the railway industry. But the way the industry has gone, I think, and I'm not really much of an expert on the modern railway industry, is that the chemistry will still be there. I mean, I came down, I live right up almost near Scotland. I came down today on a Pendolino train from Penrith. It tilts by a hydraulic mechanism. I cannot believe that the hydraulic fluid has not been developed with a chemist involved. But it's not a chemist employed by the railways, it's probably not a chemist employed by the company that made the train. It's somebody else further down the line. But chemists will still be involved. There were guys mending the track with, these high-vis jackets. Chemists will be involved there. Chemists will be involved, they're involved in everything. Of course, that's one of the messages chemists are always trying to put across. We're not just, or we're not at all, not just, we're not evil men and women hell-bent on in poisoning the environment. We are an absolutely crucial science in just about every technological development. But really, the role of the chemists is, I think, as hidden as it's ever been, which doesn't, in a way, help the case that, as Colin was saying, it doesn't actually help the case to show how important chemistry is to the railway industry and indeed to everything else. And you drive your motor car, you take a flight on the plane, chemistry is there, it's there, but it's a bit hidden. I think in a sense, that's almost, you've put your finger to some extent on chemistry's problem.
We want to take one last question. Gentleman there with hand up. Unless I've missed anyone.
It so happens, the name is Frank Grossman. It so happens that as a mechanical engineer, I was involved for quite some time on the government side on aspects of the transport of hazardous materials, including railway transport. So I was delighted to hear what we have been presented tonight. And the question is whether you see the scope for highlighting the present and future scope for cooperation or collaboration between engineers and chemists.
I didn't hear scope for future collaboration between engineers and chemists, and the example given was related to carriage of high hazard goods.
So is the scope, is that? Well, yes, there will always be such scope. Well, there must be such scope. If chemists are not involved in transport of hazardous goods, then the consequences could be very serious. So yes, what we've described, the contributions of chemistry to the railway industry, still go on, but as I said before, in a rather a covert and not very obvious and not very well known way. But certainly that role is always going to be there and must be there and vital, and that role is really vital.
And they're also wanting to be available to be consulted when problems arise in this or that. It's often the chemist who has to deal with them. And I'm thinking of the case or the example of the piano cases. A piano with beautiful casing was transferred by rail from one place to another, and unfortunately something happened, and the veneer, I suppose it was, came off, and there was a huge consultation, and I can't remember the outcome now, you can perhaps, as to whether this was due to the railways and whether the chemist could say, yes, it was that source of problem or some other. And
can I just come in?
How did it end?
Well, just going back to Colin's case, the pianos, that was a long time ago, but they find these very expensive pianos, grand pianos, were being transported by the railways, and when they got to the other end, all the pegs were rusty, and the beautiful walnut cases all had a milky bloom on, and so on. So the chemist, who was actually Jenkins at the Great Eastern Laboratory in Stratford, did a very lengthy series of experiments of replicating the conditions inside the deal boxes on which the pianos were being transported. And he showed that because the deal boxes did not have a thin lining of lead or tin that, like tea chests used to have, then moisture was coming off the crude deal cases and condensing on the pianos and causing the problem. But it does prompt me just to mention one other thing very, very quickly, that the way these laboratories changed after grouping in 1922-23 was that the chemists ceased to be the maids of all work and the jacks of all trades. Prior to 1922-23, any science, anything technical outside the realm of the engineers, that was chemistry. So chemists did bacteriological investigation of water. They did metallurgy. They even were involved in transportation of pigs by the railways and so on. After grouping, then, and this kind of thing of pianos wasn't chemistry at all. but sent it to the chemist. After grouping, with these four huge groups of LMS, LNER, Southern Railway and Great Western, then the laboratories could specialise. So you've got these more specialised laboratories developing. Lubrication was one that Colin referred to. So the chemists, there ceased to be so many people called chemists. You had soil mechanicists, you had textile technologists, you had polymer technologists as time went on, and so on. All these specialisms would have been under the umbrella of chemistry beforehand. So, I mean, inevitably science has got more and more subspecialisms, but this happened very much in the railway industry after 1922-23 when grouping occurred.
I think we can break now, and it falls on me to offer some thanks to our speakers. Obviously, questions can go on informally after this. Certainly, the flag of chemistry has been waved enthusiastically, and we've learned strongly about the period of the great chemistry laboratories within the old railway companies and the 1860-1922 type period, when certainly, even if the chemist wasn't king, the chemist was important to the development of the railway. And I think that's come across very much from the two presentations. Today, perhaps, we live in a different interdisciplinary and multidisciplinary world, and you have to delve a little deeper to unpick the contribution of chemistry, but certainly that contribution remains, together with the different kinds of engineer and other technical and scientific support people, who I suspect the passenger on the train doesn't really give much thought to unless something goes wrong. Then, if the train's late, I think we blame the engineer and not the chemist. Thank you.
I'm going to sit here and sign books. You didn't mention it.
Yeah, okay.
Sitting here and signing books.
I don't. Immediate. I think that's
Yeah, that's
I think that's the
more important.
the immediate outcome. Are you suffering badly with your leg, Colin?
Well, not really. I had an antibiotic for something else, and the after effect was a sort of detoning of all sorts of muscles. I mean, it's going.
Is this a recognised side effect?
Oh, yes. Yeah. Horrible stuff. And anyway, the thing is, it gradually goes. It takes time. And, I was a bit wonky. I've got a new knee, but that's not a problem.
Well, that's engineering.
Well, we're going to... Right.
My name is Alistair. When you started, you came to my house. We spoke about source material. You did it justice.